Okay, so what we're looking at here is the spreadsheet that is part of your homework, and I'm just going to walk through this with you right quick. In our first worksheet down here, the Tmdl Example, we've got Cottonwood Creek with a narrative at the top, and then with some calculations of sediment load, and then with some Tmdl load calculations at the bottom. And so if I can zoom in here so that you can see this a little bit better, a wastewater treatment plant is a type of source, and we might think about that. You might have a pipe coming out, and maybe 30 liters per second is the flow, and you might have 20 milligrams per liter of sediment coming out of that, and it might be steady all year. Stormwater runoff we would think about in a different way because it's associated with events, and so you might have 5 events per year that produce 2 cubic meters per second of runoff for 1 hour and 650 milligrams per liter in that runoff of sediment. Eroding banks we think about differently still because we might think about the length of the bank that we have and the amount that we're losing per year. So if we've got a 1 meter tall bank eroding and 20 centimeters per year being lost off of that bank, and the bulk density of the soil or the weight per area might be 1.5, then we could calculate that into 300 kilograms per meter of eroding bank per year. And maybe we have half a kilometer of eroding bank along a stream. Forest roads are still different, even still, and we might think about this in terms of the length of road that is eroding. And so what I've done here is just said 20 liters of erosion per meter of road, which is, and if we think about the same bulk density, so a liter again is 10 centimeters by 10 centimeters by 10 centimeters, and if we have, so that those numbers translate into 30 kilograms per meter of eroding road per year, and if we have 20 kilometers of eroding road, then we can get to the number in the calculations down below. Natural background, one way to think about that amount of sediment movement might be that the annual average of the sediment concentration in the stream is 3 milligrams per liter perhaps, and then we'd have to know the average annual discharge in Cottonwood Creek is 3 cubic meters per second, or 105 CFS, and so that can get us at what the natural background load is. So all of these are different types, numbers with different types of units, and in watershed management we need to be able to think about all of these different types of sources in the same terms and compare apples to apples. So if we come down here to our load calculations, we've got our 4 different types of human loads and then our natural background. And what I've done is just walked through a dimension analysis oriented approach for calculating loads of sediment coming off of each of these. So again, the conditions that we would think about to quantify the sediment loads here are very different because they're very different types of sources, but we need to get them all into the same unit so that we can figure out where we want to put our management. Where do we get the best bang for our buck in addressing sediment loads to a stream? And so we want to get everything into kilograms per year. And so again, for the wastewater treatment plant, we said that we had 30 liters per second of discharge, and so I've got 30 in the numerator and 1 in the denominator for liters and seconds. And so I've tracked these numbers here in individual cells so that we can easily do math and then manipulate them to think about scenarios. With the wastewater treatment plant, we said that we had 20 milligrams per liter of sediment. We said that that was flowing all year long, so 365 days per year. And so that gets us, so I'm going to use strike through here to cancel the units in the numerator and the denominator. So liters top, liters bottom, we can cancel those. And now we're in units of milligram days per second year, which doesn't make any sense, but we've got units of time in the numerator and the denominator, so we can get rid of those. And we also have milligrams, and we want to get to kilograms, so I've got 1 kilogram for every 1 million milligrams. that I've added in as a conversion unit here, and then I can strike through the milligrams and the milligrams, and then I've got these 2 units of time, a unit of time in the numerator and the denominator. So if I convert, so I've got days in the numerator, so I need it in the denominator. So days, I'm going to put down there. I'm going to put seconds up top. And then I need this to the conversion unit there, so I've actually just calculated that in this cell, that to get to seconds in a day, there's 60 seconds in a minute times 60 minutes in an hour times 24 hours in a day to get that 86,400 number. And then, let's see, so I can now checking what my units are. I've got kilograms per year. Right, so that's what I wanted to be at. And then if I scroll over here to the math, my load is multiplying all of the numerators and then dividing by all of the denominators. And the way I've done that is put the denominators in parentheses and multiply them together. So you can use the double check on your cell reference here to make sure that you've gotten everything that you intended to. And that is calculating the load then for the wastewater treatment plant. So I'm just going to zoom back out a little bit so that we can see that here. So that's the first one, first one of my sources. I've got a slightly different situation for the municipal stormwater runoff again, because we said that we had 650 milligrams per liter and 2 cubic meters per second, but that's only produced for 1 hour per event and 5 events per year. So I've already done the strike through here on this and canceled out my my units, and again over here I've added in the necessary conversions to get me to what I want. So I had I was in milligrams and I wanted to get to kilograms, so I put I had milligrams top, so I put it on the bottom, kilograms on top, 1 kilogram per million milligrams. I was in I had units of volume on the top and the bottom, so I can cancel the volumes out, meters cubed and liters, and I just need to come up with the appropriate conversion. So again, put meters on the bottom, so it'll cancel with meters on the top over here, 1 cubic meter per every 1,000 liters, and then I have got both seconds and hours in here, and so I put seconds and hours here, and again just did the calculation, 60 times 60. And then again with the math, I multiplied all of the numerators and then divided by all of the denominators, and I get to my kilograms per year, and this number then gives me the load from municipal stormwater runoff. And then the same thing I did for eroding banks and Forest Service roads, and you can look at the cell references there and see how that was done. It was done the same way. So if I zoom back out now, then I'm going to reference these numbers that I've calculated up there for my, so I guess quickly looking at natural background, I said I had 3 milligrams per liter and my annual, as an annual average, and I've got 3 cubic meters per second as an annual average flow. Then I need to get from seconds to years, and from meters, or cubic, from liters to, and meters need to cancel out, and kilograms to milligrams again, and so I come up with my natural background sediment concentration here. And then scrolling down here, I've got my sediment load limit, which I've set up here in my narrative. Just for simplicity, I've said that the Tmdl process has determined that the sediment load that Cottonwood Creek can carry before its beneficial uses start to get impaired is 1.4 times the natural background. And so to calculate that, I've got 1.4 there. So this is my sediment load calculation here. The math is over here, and it's referencing that 1.4 number and multiplying it by the natural background. And yeah, so zooming back out here so that you can see that. Yeah, so my calculation here is referring to the natural background of sediment and my ratio, and I'm saying the load limit that it can handle is 397,000 kilograms per year before it gets impaired. So I have consolidated this table a little bit here so it's easier to see now. And so my sediment load limit again is natural background cell reference that I calculated up there, the annual load of sediment times this 1.4 ratio. A margin of safety is used in the TMDL, which is typically 10%, and so this simply references the load limit and takes 10% of that, and then the total available amount of sediment that I can allocate to my human point sources is the load limit minus the margin of safety. So that's calculated here, and I've totaled up what my point sources are from above and my anthropogenic non-point sources, and my load that needs to be reduced then is my current load minus the load limit here. And so the current load was totaled up above right here, and my load limit is calculated, and now so I need to reduce by 238,000 kilograms per year, which is a 40% reduction. And so I could think about a 40% reduction across the board, or I could get strategic and start thinking about reducing my non-point source loads, which are much larger than my point sources, because typically non-point sources can be cheaper to address than point sources, where often a lot of technology has already been implemented. So this spreadsheet is a way for you to calculate the loads and think about your dimension analysis with this numerator-denominator strike-through approach, and hand it in so that we can see how you did it. And the nice thing about this is that you're going to be able to come in and then change the amount of each one of these types of pollution sources, change the length of eroding banks or the load per bank if we stabilize the banks partially, or if we reduce the amount of eroding banks, or if we reduce the amount of eroding Forest Service roads. We can roll through different scenarios of sediment pollution reduction and think about the costs associated with those and really put things in context from a management perspective. So that's the first worksheet. You'll have two worksheets in your Excel spreadsheet. This is very parallel for Skunk Creek. We have the narrative up here describing the different types of sediment sources to Skunk Creek and the data about the amount of sediment coming in terms of the way that you might collect the data. And then this load calculation area down here is blank. Again, it's largely parallel, so you can draw on the example, but there are some differences that you'll have to pay attention to. The wastewater treatment plant only discharges for half the year, and a few additional things like that. You can look at the cell references again in the example to figure out how to calculate these things, and then roll through the scenario for load reduction as outlined in the homework. So there is an additional Camtasia video that walks through a simple example of this dimension analysis. So if you're not comfortable with dimension analysis and want a little bit more discussion of that, then see the other Camtasia video with a few simple examples that are handwritten so that you can go through the process a little bit more intuitively. And otherwise, good luck with the assignment. Have fun.